This lesson is for advanced algebra. We're going to do a combination today of 9-1 and 9-2. 9-1 is on exponential growth and 9-2 is on exponential decay. Students will need a minimum of a scientific calculator here, so most of you will probably just simply use your graphing calculator for this lesson. In both lessons, you're going to be working with the exponential equation called ab to the x. It's called exponential because the variable x is a power or an exponent. The three parts of the formula are value A, which represents the initial amount, sometimes called the starting amount. When you graph it, the A value is also going to be where the graph crosses the y-axis, or the y-intercept. The B value is referred to as the growth factor, and we'll talk more about that shortly. The x, the exponent, is going to be your variable, so usually the x will stay as a letter. Sometimes it'll be a number, but it represents the time, which is usually indicated in years. If it's not indicated in years, then you'll have to turn it into a fraction. So when a population is growing, we call that exponential growth. And the word problem that goes with it will use words like the population is going up or increasing, or the value of the item is appreciating in value. When you're working with an exponential decay situation, that means the population or the item that you're working with, the house or the car, is going down or decreasing in value or depreciating in value. So the growth factor is what's going to determine if it's a growth or decay situation. Most of the time when you're working with either growth or decay, the amount of growth or decay will be indicated by a percentage. So when you take that percentage, usually you're going to change it to a decimal. If it's a growth situation, you'll add 1 to that decimal. If it's a decay situation, you'll do 1 minus that percent. And we'll practice some of those here in just a moment. Another thing that might happen when you're working with growth is instead of a percentage, it might indicate that it's the population or the item's value is doubling or tripling. In those cases, you would simply use a 2 or a 3 for your B value. I also want to look at what these look like when you graph. So AB to the x, when you graph it, is going to be called an exponential curve. So both graphs here, whether it's growth or decay, is going to be called or referred to as an exponential curve. You can see that it's either going to go up from left to right or down from left to right. It'll go up from left to right when it's growth. It'll go down from left to right when it's decay. So if you look at the equations that are given in both situations here, you can see that the A value is the value 10. And if you look at the hashtags or hash marks here, you can see that 10 is indeed where it's crossing the x-axis. The B value here is indicated in parentheses, which oftentimes happens. It's also the number that has the x with it. The number here for B is 1.2, so somebody took 1 plus the percentage and that's what they got. So clearly this came from a situation that was growing or increasing 20%. If you take 20%, turn it to a decimal, add a 1 to it, you're going to get 1.2. So that's what growing 20% would look like as a growth factor. Let's look at the decay curve. This one's going down from left to right, and the equation for that, again, crosses at 10. So the initial value for both of these examples is the same. But this time the B value is now 0.8. If you have a number less than 1 for B, it's going to be a decay situation. So then you got to figure out how much is it decaying. So this situation would have been, or this 0.8 would have been found by taking 1 minus some percent and getting 0.8. So I usually think about these as money situations or dollars and cents. So if I have $1 and I take away a certain amount of cents and I'm left with 80 cents, that means that 20 cents was taken away. So in this case, change that to a percentage. That would have been a 20% decay situation. So this one was going down 20%. So that's what the B value would look like if that were the case. So those are a little bit more difficult to figure out because you can't see the percentage in the equation itself. You have to figure out what it would have been prior to that. Both of these graphs are called exponential curves. They have one other characteristic that's the same. They both have something called an asymptote. Notice that the P there is silent in the middle, and the S here is pronounced a little bit more like a Z. So an asymptote is what the graph approaches but never reaches. So you can see here that in both graphs, they're going to get really, really close to the x-axis but never actually cross over it. And so we indicate that on a graph usually with a horizontal dotted line. So if you're asked to give the asymptote for an exponential curve, you're going to say that it's either the x-axis, if you're describing it in words, or if you are asked to give the equation for the asymptote, you'll say y equals 0. So let's practice the equation a little bit further. If we're looking at these 4 examples of 4 exponential situations, 2 of them are growth and 2 of them are decay. So let's take a look at the top 2 here, examples A and B. In both situations they have an A value that's listed and a B value that you can identify, one of them in parentheses, one of them not in parentheses. Whether or not it's in parentheses doesn't mean anything, it's just sometimes it's put in parentheses like that. So you can see here that the B value is a 3, so that means this would have been a growth situation because the B value is a number greater than 1. And in fact, this word problem that came from this would have mentioned the word triples in some fashion, because the B value here is a 3. So the growth rate here is tripling. And then the A value, or the y-intercept, is going to be the 200. Same thing for B, we've got an A value of 100 this time, so it's going to cross the y-axis at 100. And this one was also going to be a growth situation, but this time it would be indicating that it is doubling, or that the population is doubling. The bottom 2 examples, for examples C and D, are both decay situations. So in C we've got another 10 for the A value, and then because it's a number less than 1, this has to be a decay situation. So we have to think about what minus 1 minus what percent is going to be 0.75. So think about it like a dollar minus how many cents is 75 cents. Hopefully that's clear that that would be a 25% decrease. So we'd say this is a decay situation going down 25%. Use a similar method to figure out our last one here for D. The A value is a 50, and then 1 minus some percent gives us the 0.6 for our B value. It's a number less than 1, so it's got to be a decay, so it would be going down from left to right if we graphed it. A dollar minus what is 60 cents? That has to be going down then 40%, or 0.4. So now let's try exponential growth and decay in a word problem situation. In 1993, the U.S. population was 258 million. During the 90s, the population grew 1% annually or yearly. Estimate the population in 2076. It's a good idea to write down your formula here. Even though it doesn't say that it's exponential, you can usually assume that populations will be exponential unless they're indicated otherwise. So we know our formula is going to be y equals ab to the x. We need a starting value for the A, which in this case is 258 million. You can either add on 6 zeros or just remember that you're going to be using the word million with your answer as a label. The B value, we need to figure out if it's growing or decaying. Clearly it's growing by 1%, so we're going to change that number to a decimal first. Be careful here, it's not 0.1, it's 0.01. 0.1 would have been a 10% increase. So then if it's growing, we want to add a 1 to that number. So our B value then is going to be 1.01. If we just multiply by 0.01, the number is actually going to go down. So we have to take that 0.01 plus what it was originally, which was a 1, and add that in. So that's why our B value is higher than 1 here. And then we're going to raise to the time, and the time is indicated by the years subtracted. So we want 2076 minus the 1993, which was the starting date. Make sure you subtract before you calculate there. So you've got 2 options for how you can type that in on your calculator. You can either type it in as we've already written it, or you can say 258 times 1.01 to the 83, because that is the difference between the years. So you go ahead and you type that in on your calculator. And when you type that in, you get about 589, making sure to put back that word million in your answer. We did round it off to the nearest whole number here because it's population, so know that if you were asked to round to the 10th or the 100th, that would change our answer, of course. Now let's talk about how we would answer the follow-up question. In what year will the population reach 500 million? So now we're trying to get to 500 million from the equation that we were already using, but now the time is the unknown. Remember that the time is going to be in years, so we'll need to add that back to 1993 when we're all done. So really it's going to be what minus 1993 to help us figure that out. Now currently students will need to use the method of trial and error to determine the answer. Later on in the chapter we will learn how to actually solve this equation. It's really hard to solve for x right now with the tools that we currently know because x is an exponent. So we're going to be learning something later on in the chapter called a logarithm, which will help us get that x solved when it's an exponent like that. So students right now need to just type in what's on the right and guess on a number for x until they can get as close to 500 million as possible. Keep in mind that you can kind of predict that it's going to be a number smaller than 83 because we know that 83 is going to generate a 589, which is too large. I will give you a hint here, it's going to be a number in the 60s. Pause the video and go ahead and give that a try. So if you go ahead and calculate this out, you should have gotten the x to be between 66 and 67 years later. So if we add that onto the original time, which was 1993, we get the year 2059 to 2060. So students could say either one or the other, or say that it happens somewhere between those 2 years. So that was a growth situation. Let's try one that is decay. In 1988, a new Pontiac Trans Am was $15,798. Suppose the car's value depreciates 13% per year. Most cars do depreciate in value, by the way, and they do depreciate usually much faster than that. Write an equation that illustrates the above situation for years after 1998. Students need to know here that writing the equation could be something that you'll be asked to do. Simply set it up rather than calculate. So again, here this is a depreciation value, so we know we're going to be using exponential equation. And they do say equation, so make sure you include an equal sign in your answer. So the starting amount is given, that's 15,798. The b value we're going to have to determine. Remember, it's a depreciation, so we need to do 1 minus the percent. Percent would be 0.13, 1 minus that is going to be 87% or 0.87. And then we'd raise it to the time. And the time is going to be years after 1988, so we're going to include that as our variable. If you just had it raised to the x, that would be perfectly fine as well, but then you'd want to write a note that the time starts at 1988. Now that currently is not truly an equation, so we'd want to make sure to set it equal to something. I'm just going to set it equal to y so that it matches with the x. Now if you're trying to find the car's value in 1995, we'd need to figure out how much time that would be. So we would calculate there, or we could simply fill in 1995 for x. So either way would work there if you figure out how many years that is, or fill in 1995 here and calculate on your calculator. You'll eventually be typing in 15,798 times 0.87 to the 7. Make sure that when you're working with money that your answer has 2 decimal places that you round to. So we're going to say here 5959.871, and so this 1 here is what's going to determine if I keep the 7 the way it is or raise it up or round it up. The 1 indicates that the 7 is going to stay put. So I put a dollar sign, 59.59, and 87 cents is my final answer. One final topic that I need to mention to students is sometimes half-life is a topic that you're going to encounter. Half-life will probably be something that you would see again in your science classes here at Edina High School. A common decay situation involves radioactive elements in the periodic table. One that comes to mind for me is plutonium. That's the main ingredient they use in atom bombs, and it is radioactive, which means it does have a half-life. The half-life of a substance is the amount of time it takes for half of the substance to decay. So when you're working with a half-life situation, notice that the exponential equation changes. Now it's no longer ab to the x, but simply a times a half to the x, the half representing the half-life. Now be careful here because the exponent is going to change slightly from what we're used to on the regular exponential equation. The x here could be or represent the number of half-lives, or if you're given it in time or length in years, you'd want to divide the years by the length of the half-life. So let's just do a quick example here to illustrate how to use the formula. Strontium-90 is an element in the periodic table, and it has a half-life of 29 years. If you start with 1,000 grams of that material, how much will remain after 10 half-lives, and how much time is that? So we've got a starting amount, that's our A value of 1,000. We're going to keep the B value at a half, or 0.5, you can use either one there. And then we're going to raise to the, it could be number of half-lives, so we could raise it to the 10. Or if they gave us a total length of time, we would divide it by the 29 to figure out how many years that is. So we're just going to type that in on the calculator, and when you do that you get about 0.98 grams, depending upon what they ask you to round to. The amount of time that is, if it's 10 half-lives and each one is 29 years, that's simply 29 times 10, or 290 years. So if they told us to calculate this for 290 years when the half-life is 29, we would raise to the 290 over 29 for the exponent instead.